In this video, we'll be going over the answer key for Wednesday, April 8th. And what we're talking about at first are solubilities. So there are some compounds that are not soluble. We say they're insoluble. However, every ionic compound will, to some small degree, be soluble. And we can think about this in terms of equilibrium. So silver chloride, which is technically, we would call that insoluble, but it still breaks down a little bit. It'll break down to silver and chloride. And we can make an equilibrium for that, where it's products over reactants. Silver chloride is a solid, so we don't add that in. So our equilibrium constant is just a concentration of silver times chlorine. When we're talking about how much an insoluble product breaks down, this is called KSP. This can also work for a soluble product, but anything that's dissolving, the equilibrium constant is called a KSP, or the solubility product. Now, how many moles of silver and how many moles of chlorine will break down during this? That's what we call molar solubility. So if we were doing an ice table, X, the change in silver and chlorine, we call that molar solubility. So let's take a look at a problem here with that. So we have lead fluoride. Lead fluoride molar solubility is 5.63 times 10 to the minus 3. So I want to know what the KSP is for this compound. So we can set up our equation. PbF2, which is a solid, breaks down to Pb plus 2F. And we can write our KSP for that, equals lead times F squared. Remember, if you have a 2F, that's actually F squared. When we're doing our ice table, since our solid's not in our KSP, I don't care about that column, so I just cross it out. And we start with no product. Imagine we just dropped this solid into the water, so we don't have any product yet. So 0 and 0 for lead and fluoride. We're going to make product though, so plus X plus 2X. So at equilibrium, lead will be X, F will be 2X. We take our equilibrium row, plug that back into KSP. And so remember, it's 2x, and I actually wrote the square wrong. The square should be on the outside like we see in this top line. So KSP equals x times 2x squared. Well, 2x squared, if the square should be on the outside, remember, it's actually 4x squared. So KSP equals x times 4x squared, or KSP equals 4x cubed. Now, we know what the molar solubility is. We know what X is. It's 5.63 times 10 to the minus 3. So 4 times 5.63 times 10 to the minus 3 cubed is 1.7 times 10 to the minus 7. So that's our answer for that problem. Question 2, if we're doing the reverse now. So barium fluoride has a KSP of 2.45 times 10 to the minus 5. What's its molar solubility? But there's a caveat now. So we're mixing barium fluoride with compounds that are already soluble. In problem A, we're going to consider if there's barium nitrate in there, and even though I wrote C, this is actually B. We're going to imagine if we're trying to dissolve barium fluoride in sodium fluoride. So how does this change any calculation? So we're just going to focus on A here. So barium nitrate, or nitride, it's nitrate. Barium nitrate will break down to Ba plus NO3. I wrote NO2 down, but that's actually NO3, but that actually doesn't matter all that much. So all of this will dissolve. So if you were to do your ice table, you start with 0.1 barium nitrate, and it all broke down. So you have 0.1 barium and 0.1 NO3. All right, so that's in your solution to begin with. Then we take this barium fluoride and drop it in. So our barium fluoride will break down to barium plus 2 fluorine. So we can set up our ice table for that. Again, we have a solid here. Now we already start with 0.1 barium. That 0.1 is coming from barium nitrate already being dissolved and already adding 0.1 barium to our solution. All right, So 0.1 barium, no fluorine, so we're still going to make products. The change is X and 2X. 0.1 plus X will make 2X, all right? And we can set up our KSP. So KSP equals 2.45 times 10 to the minus 5. That's from the problem. And our expression for KSP is just our products again. So KSP equals barium times fluorine squared. Now, we have a plus X here, but our equilibrium constant is much smaller than our starting concentration. Starting concentration is 0.1. KSP is times 10 to the minus 5, so 0.1 is 100 times bigger than this. So I can ignore this plus X safely. Now I can say KSP, which is 2.45 times 10 to the minus 5, equals 0.1, which is barium, times 4x squared, which came from fluorine. Solve for X, and the molar solubility of barium fluoride and barium nitrate is now 7.55 times 10 to the minus 3. So that's called the common ion effect. Basically, if you tried to dissolve something that's insoluble in a solution that already contains one of its compounds, it's going to be less likely to dissolve because of this equilibrium balance. This whole equation here is telling you how much barium fluoride will dissolve. Well, we already have barium, so this X is actually going to be less than what it should be normally. Now, we've been talking about insoluble things. There's also another type of constant called formation constant. So let's say that you have silver and NH3 in solution. They will make silver NH3 because this compound is insoluble. But you'll form the aqueous version super quick. And the formation of that is called a KF, right? So KF equals the products of the reactants again. Here we have aqueous, so we can put that into our equilibrium constant. Basically, anytime I tell you a KF, the product you're going to make is aqueous. So let's take a look at how we use that. So we have a solution that's 1.1 times 10 to the minus 3 molar zinc nitride and 0.150 molar NH3. After our solution reaches equilibrium, how much zinc is left in our solution if our KF for this zinc NH3 compound is 2.8 times 10 to the 9th. All right, so here's our overall equation, what's happening. Zinc plus 4NH3 makes zinc NH3 4. Our KF is products over reactants, as here. Now, before we go and solve this, we have to look at the other, what else is going on in our equation? What other compounds are in our solution? So if we have zinc NO3, this will break down to zinc plus 2 NO3 minus. We initially started with 1.1 times 10 to the minus 3 of this compound. It will break down completely, so we have 1.1 times 10 to the minus 3 zinc. And we also start with 0.150 molar NH3. So now we can set up our ice table, because we have our initial concentrations. This 1.1 times 10 to the minus 3 from zinc NO3. This 0.150 from our NH3. And we have no zinc NH3 yet. We haven't made it yet. So our change. So this is going to be different than what we've talked about. So our KF is a massive number, times 10 to the minus 9. That's in billions territory. So the numerator is going to be massive. And our zinc concentration starts off very small. So if your K number is very big and one of the reactants is very small, you can assume that like 99.9% of this reactant will react, even more, like 99.999%. Not all of it, not 100%. You're still going to have some zinc in solution. But I'm going to assume just about all of this will react. So the assumption I can make is that for my reactant that is the smallest number, if my Kf is big, I basically lose all of that in the reaction. So my change is negative 1.1 times 10 to the minus 3, which is the same number as my initial zinc. That change will be constant for all my C's. So NH3, there was a 4 in front of it. So I have to do minus 4 times 1.1 times 10 to the minus 3. My zinc, it's plus, so plus 1.1 times 10 to the minus 3. At equilibrium, so this is also different. Normally, I've been telling you that the ice table is a ledger. Whatever C is, will give you E. So if we were to do that, I minus C is 0. However, like I said, you won't have 100% of your zinc be gone in this reaction. You're going to have a very small amount of zinc left. So we have to figure that out. That's X. However, in these columns, the NH3 and the zinc NH3 columns, I can be confident that this math is correct. The error is going to be so small, I don't need to worry about it. So at equilibrium, we have 0.1456. Equilibrium, we have 1.1 times 10 to the minus 3. All right, we have everything we need to solve for X now. We have Kf, which is 2.8 times 10 to the 9, equals zinc NH3, which is 1.1 times 10 to the minus 3, divided by zinc, which is X, multiplied by 0.1456 raised to the power of 4. The reason why I always write out Kf in variables is because it's very easy to forget this power of 4. So as long as you write your Kf in variables like this, you should, if you follow this, have no problem getting the right answer. And so we solve for X. X equals 8.7 times 10 to the minus 10 molar. And that is it for today's questions. As always, if you don't understand something, please don't hesitate to email me, and I'll see you in the next video.